All right, so now that we've seen an implementation of this merge sort, let's actually jump back to this kind of question about the running time of this particular algorithm. Earlier, I kind of gave us this kind of hand wavy version of like, okay, it feels like it should be about n log n. What I want to do now is I want to kind of double back and kind of make sure that that is definitely solidified. So what I like to do here is I'm going to start with kind of little baby examples of like, let's say I have just the list 8, 6. I rip it apart into an 8 and a 6, and then when I glue it all back together, that's going to have two comparisons. So lists of length 2 would then have two comparisons to actually fully sort this thing. The 6 and the 8 bring the 6 over, ultimately bring the 8 over. Great. You can kind of think about that as my starting place. And as we'll see in a little bit, there's a little bit of induction that can live behind the scenes as well. So this is really going to be where I start things off. If I up the ante just a little bit more, so if I have the 8, 6, 7, 5, so now I have a list of length 4, I rip it up into a whole bunch of little pieces. And then when I begin the sewing process, that's where my comparisons are going to begin to take shape. So I have the 8 and the 6. I know that that's going to take two comparisons. I then have the 7 and the 5. That's also going to take two comparisons. So this whole row is then going to require 4 comparisons. And 4 is actually the length of my original list. So every single row should have n comparisons, which we can see actually occurs. So in the next level, when I have list 6, 8 and list 5, 7, I grab the 5, I grab the 6, I grab the 7, and then I grab the 8. So there's going to be 4 comparisons there as well. So in total, I get 4 plus 4 or 8 comparisons. And what you want to think about this is really that's going to be computed by saying 2 times 4. So 4 is the n, and 2 is the exponent that comes from the length of the n. That process then continues if I were to look at a list of length 8. So I'd have 8 broken into 4s, broken into 2s, broken into 1s. Then the 1s get re-glued into 2s. That's going to require 8 comparisons. Then the 2s, so some Spock hands, then get converted into quads. Those two groupings then are both going to require 4 comparisons for a total of 8. Then I got the quads, which is going to turn into one big group of 8, which is then going to also require 8 comparisons. So 3 rows, all of which are going to require 8 comparisons. So in total, I get 3 times 8 comparisons. The 8 is my n. The 3 is the exponent that exists on that n when I view it as a power of 2. So it's an n and a log base 2 of n. So it's this cute little chopping aspect that requires us not to have n rows, but only 3 rows, or log base 2 of n number of rows. So it's this efficiency game that we get is that we're doing a bunch of things all at once. So I don't have to read across this thing one by one. I can do, 8 things down into 4 things fairly tidily. What we start to see is that we know that there is this recursive implementation of this thing, but there's also a recursive way to actually count the number of comparisons. And that's where we can start to see the nice blending of the structure of the algorithm coming into the actual runtime. So here we had the number of comparisons for a list of 8 entries. If I wanted to up the ante and actually look at a list of length, let's say 16, if I wanted to count how many comparisons that's going to take, what I'm trying to compute is I'm trying to compute t of 16. So t of blah is then going to represent the number of comparisons it takes to sort a list of length blah. What we can see is that my very first move would then be to take this list of length 16 and then chunk it into 2 lists of length 8. Well, we know the number of moves it takes to sort lists of length 8s, so shouldn't we be able to lean on that a little bit? And that's exactly what we want to do, is that to sort a list of length 8, it should take t of 8 steps, which is what this answer just computed. So t of 8 is 24. I have to do that twice, so I have 2 of those. Now I'm sitting with 2 blocks of length 8 that then need to be glued together. So what I need to see is I need to see 16 additional comparisons to actually sew everything back up. So what you can see is this really nice recursion that's going to take shape in this count of the number of comparisons. In the same way that we saw it in the implementation, is that we back called MergeSort over and over and over again. So each run we had to call MergeSort twice. So here you can see that that's going to come into play very nicely on the counter as well. If I wanted to see how many comparisons it's going to take for a list of length 32, well, it's going to be, well, 2 copies of lists of length 16, and then ultimately throw all of those together in one big list of length 32. In general, if I wanted to sort a list of length n, it's going to be, well, how much does it take to sort half of it? Do that twice, and then re-sew everything back together with the little n at the end. So what you can start to see is that there's this really nice recursively defined sequence taking shape. It starts with t of 2 being 2, and then any subsequent one is just going to be based off of the previous ones. So you can actually see this little counter emerge really nicely in that I have t of 2, which is 2. If I wanted to compute t of 4, so the number of comparisons for a list of length 4, well, it's 2 times t of 2 plus 4, which is 2 times 2 plus 4, which is 8. And if I go back to my example, that should hopefully match up. So when I had a list of length 4, it required 8 steps. If I then want to go one step farther, I'm going to have t of 8, which is going to be 2 t of 4. So break it in half, sort those halves, and then ultimately glue them back together afterwards. So counterwise, that would be 2 times 8 plus an 8, which should ultimately end up being 24. If I wanted to do this t of 16, that's the one I kind of alluded to. It would be 2 times t of 8 plus a 16. So that's going to be 2 times 24 plus 16. What's that going to be? 48 plus 16, which is what? 64. I think. I hope so. So this gives me a recursive way to count the number of comparisons, which is sometimes the really easy way to do the count, is that you're designing this thing and you're like here and here and here and here and here, and everything is great. What's really nice about all of this is that once you have this recursively defined way of counting, we can invoke a little bit of induction. So if you remember back to your Math 201 days, you can actually take this type of shape and actually get an explicit answer from it. So back here, we kind of guessed what the explicit answer should be. We're like, okay, this feels like it should be, 3 layers. Each of those layers each have 8 entries. So I'm going to guess there's going to be like 8 comparisons. So let's ultimately guess that the final number of comparisons is 8 times 3, or n log n. Here we have the counter coming up recursively, and what we can actually do is we can begin to invoke a little bit of induction to see exactly what that final counter is going to be. So induction might be a super duper scary word. You hated Math 201 days, but it's a really tidy way to go from this kind of recursion, so this recursively defined sequence, into an explicit one. So in the notes, I do have a little bit of sketching out how the induction is going to go. I'll kind of just give a quick overview for how it's all going to run. So we start with the base case. Here I started with t of 1 being 0. You could alternatively start with t of 2 being 2. Sometimes that feels like the more natural starting place because I have a list that actually needs some swapping. Alternatively, you could think about a single element doesn't need any comparisons. And that's actually going to be where we start our induction. So what we do is that we're going to assume that this works at level K, and we're going to try to show that it works at the next level. So if you remember this induction as this big old ladder, well, if it works for a list of length 8, I'm then going to try to show that it's going to work for a list of length 16. So the next rung up on my ladder is going to be twice the length of the previous list. So I have my goal of trying to show what it's going to be, and my assumption is that it does work at level K. After that, you're basically going to use this equation that we had before, do the back substitution, and then a little bit of kind of arithmetic logic to kind of sew all of those things back together. I'm not going to go super far into the induction. I'm not going to make you do that in this class or anything like that. But if it's kind of eating in the back of your head of being like, I've totally seen this before, it's because you have. It's the exact same way that we counted in 201 is now the way that we're going to count here as well, is that you can kind of see these pieces all come back together. If you wanted to, you could go super far into the induction realm. I'm going to be totally happy if you can kind of look at these things and get a count of being like, okay, n across by 3, that's going to be n log n. If you want to, though, there is a little bit more formal stuff behind the curtains, so you can definitely take a peek at what's going on there. If that scares you to death, just pretend that those slides don't exist and then make me really sad, I guess. But it's fine. You don't have to kind of remember all of those subtle little nuances. But I would recommend maybe taking a peek and just making sure that the algebra all checks out and kind of how those pieces all go. It should hopefully feel very natural, is that this code was actually typed up recursively. There is this recursively defined sequence that tells me the number of comparisons. All of those things should begin to morph in on themselves to give you a really nice way to count the number of comparisons. So anyway, soapbox rant over. Now you can pretend that those slides didn't exist and I don't know, burn them, do whatever you want to with them as we begin to move into our new topic, which is going to be about the quicksort. So I'll pause the video here and then we'll start that whole process all over again.